So I want to finish this segment on log linear taggers with an example of a particular application that illustrates their real strengths. And this was in a paper by Andrew McCallum and others, which was another absolutely seminal reference in the use of log linear models. So McCallum and others compared a hidden Markov model and a log linear tagger on a FAC segmentation task. We'll see in a second just what this is. But the main point is that in this particular domain, modeling the conditional probability of a word given a tag is very difficult. So remember that HMMs had two types of parameters. For example, a trigram tag parameter, the probability of v given t of u, and then emission parameters, word given tag. This can be a difficult distribution to model, and it really hampers the ability of HMMs to take into account complex features when you build tagging models. So this is the FAC segmentation task that McCallum and his collaborators looked at. And so, in fact, they're going to be tagging entire lines of a FAC. So a FAC is going to be a sequence of lines, as we've seen here. We have 1, 2, 3, 4, 5, 6, close to 15 lines. Some of them will be blank, notice. We have a few blank lines here. And their goal was to assign one of 3 possible tags to each line. So a line can either be part of a header, so we have these head tags for the header of the FAC. They can be part of a question, so we have a tag here, question, saying this is a question. And finally, they can be the tag answer, if we have an answer to a question. So you can see how this is a useful task in that if you can perform this kind of tagging accurately, then you could automatically pull question-answer pairs out of this rather unstructured data that you would see in these, at least these type of FACs. So one thing that's worth noting is that each word in this tagger is an entire sentence. Okay, so we're tagging sentence by sentence. So the items that I'm actually tagging are quite complex objects. They're entire sentences. So it'll be critical in this model to make use of various features of entire sentences, or entire lines rather. So here are some features that are used in this work by McCallum and others. And these are generally binary features which will be true or false for a particular line. So we could ask whether a line begins with a number, whether it begins with an ordinal, whether it begins with punctuation, whether it begins with a question word, where these will have been a sort of closed set of words like who, where, what, and so on. We can look at whether the line is blank, whether it contains an alphanumeric, whether it contains a number, and so on and so on. So you can imagine making up a whole bunch of features of individual lines which might give some strong evidence about the content of that line, and most importantly would give strong evidence about whether it falls into one of those 3 categories, a header or a question or an answer. So we can now describe the features that we used within the log linear tagger in this work. And they're really rather intuitive. They are going to look at properties of each line, for example, the fact that a line begins with a number, in conjunction with the current tag, say question, and also the previous tag. So in this case, we're going to look at a bigram of tags. Remember, we always have the ability to look at the previous 1 or 2 tags in the context. And in addition, we look at some feature of the line, for example, the fact that it begins with a number, or it contains an alphanumeric, contains a non-space, contains a number, and so on and so on. And so this is the basic set of features which were used in the log linear tagger. A more challenging task is actually coming up with an HMM tagging model for this particular problem. Again, and this is because the quotes words in this particular application are entire lines. So how do I estimate the probability of this entire line given the fact that the tag is question? So the first method that McCallum and the others used was to break this down into a sequence of terms, one for each word. And so we'd have emission parameters where we condition each word in turn on the identity of the tag, question in this case. So I have E of 2.6 given question, so that first word, times E of what given question, the second word. And so here I just have one E term for each word in the sentence. This looks very much like a language model for each tag, for example, question. In fact, this is essentially a unigram language model, which is trying to define the conditional probability of a particular entire sentence or entire line conditioned on a particular tag. So that's the first method that these guys looked at. And once we have these distributions, we can apply the hidden Markov model tagger in the usual way. Here's the second method they used. And in this method, they took each line in training or test data and immediately transformed it into a sequence of features. So in this case, we'd have a sequence saying that it begins with number, contains alphanumeric, contains non-space, contains number, previous is blank, which means that the previous line is blank, for example. And then we again use what is basically a kind of a unigram language model, where we have one term for each of these features. So we have the probability it begins with number given question times the probability it contains alphanumeric given question, and so on and so on. So it looks very much like the model on the previous slide, but we just go through this transformation step first, which extracts the important features from each individual line rather than simply staying with the words. So let's look at the results for the different methods. And this is going to be in terms of precision and recall at recovering entire segments, where a segment might correspond to a header or to a question or an answer. So this first result, what they called a ME stateless, this stands for maximum entropy stateless. Remember, a maximum entropy model is basically a log linear model. This was a log linear model, but where there was no conditioning on the previous two tags in the context. We only conditioned, in each case, on features of the individual line being tagged. And that model performs quite poorly. That's really just evidence that the surrounding context in the form of the previous two tags is actually very useful. Token HMM is the first approach to building a hidden Markov model that I showed you in the previous couple of slides, where we simply calculated the probability of an entire line by basically creating a unigram language model which had a single term for each word in the line. Feature HMM was the second HMM solution I described to you, where in a first step we took a line and transformed it to the sequence of features representing that line, or rather representing features of that line. And we can see we get a slight improvement here. These numbers are getting better and better. And of course, MEMM is a log linear trigram tagger. And again, these things are sometimes referred to as maximum entropy Markov models. So an MEMM performed considerably better than any of these other methods. There's a very clear advantage over hidden Markov models.